Welcome back to our power system lecture series. During today's lecture or today's video, we are going to analyze the transmission line performance under long transmission line condition. Before we start, let's have a few moments to recap on what we have done in the past two lectures. In the first lecture, we introduced transmission line parameters, and we spoke about R, C, the conductance, and the inductance L. And then we analyzed the circuit for a short transmission line, which is set between 0 and 80 kilometers. In the second lecture, we analyzed this transmission line under between 80 kilometers to 250. This is known as a medium transmission line. We also explained in the previous lectures that depending on the voltage, the length of a medium transmission line could vary. Could be 160 to 50 kilometers depending on the voltage level. Let's now assume it's 250 under this certain voltage level. And a long transmission line when it exceeds 250 kilometers in distance. Now, during today's lecture, we are going to analyze the A, B, C, D parameters. The A, B, C, D parameters of long transmission line network. Let's start. Now, for a long transmission line network, let us first draft the circuit. This, I want to call it Z, but because now I'm using a long transmission line network, I need to consider, this is Z, I want to consider delta X. This is known as Vx at a point X. This value is Y at delta X, Y for a delta X. And remember, I can also include for the long transmission line, if required, I can include the conductance. I can include the conductance of this network. Now, what's Z? I consider now, I need to define Z to be equal to R plus J omega L. R plus J omega L. The Y, because I'm taking, it will be equal to, see this Y? Will be equal to G, remember the conductance, plus J omega C. J omega C, remember, I'm using 1 over X C. This distance will be X plus delta X. This distance will be X plus delta X. The idea behind the long transmission line is I will find the delta X, the small amount of variations into this network. Okay, where do I start? How do I start? Perfect. What will be this one? What will be this voltage? What will be this voltage? This voltage will be V of X plus delta X. Is that correct? See, this voltage is V X plus delta X because of the distance. If I apply Ohm's law, this voltage equal this voltage plus this voltage. This voltage plus this voltage. Let's take this to be Ix, the current. That's the current Ix. This current in here, let's take this one. This current in here, let's look at it like this, or this, depending on the movement of the current. This current will be I x plus delta x. X plus delta x. Perfect. Let's analyze the circuit now. What do I have? This voltage, it's equal this voltage plus this voltage. Let's write that down. V x plus delta x. It's equal to Ix multiplied by Z of delta x plus Vx plus Vx. Look, I can rearrange this equation to be Z Ix, it's equal to Vx plus delta x minus Vx over delta x. That's all I did. That's all I did. Is to recap. Let's go one more time over it before we go further into analysis. I set up my long transmission line to be, I have a voltage Vx at a point x, and then I have delta x distance, which represent with Z delta x. We knew from before that the transmission line, the series, is depend on its own per kilometer. So it's per distance. This distance now is delta x. Same for the capacitor. It will be a capacitor farad per kilometers. So same for the y. All I did now is I analyzed the circuit. This voltage is equal to this voltage plus this voltage. Let's say this current goes through here, So now this voltage equal this voltage plus this voltage. All I did is rearrange it into here. Do you remember the limit calculation when delta x goes to 0? So what will happen to this when what will happen to the limit when delta x goes to 0? What will happen to this system if you recall this characteristic from math? What do I have now? I have this will be dvx over dx equal to, so now this will be equal to, this system will be d of vx over dx, it's equal to z ix. It's equal to z ix. Is that clear? Now this, take a moment to digest this information before we go any further. So all we did is the derivative, the limit, we did the limit when delta x goes towards 0, which is give us that derivative of Vx. Perfect. This is based on KVL. Let's now do KCL on this node. KCL on this node. Let's write this in here. I have the derivative of Vx over dx, it's equal to z ix. Let's remove this. At this node, what do I have at this node? Let's use different color. I have this current, it's equal to the current that goes down plus this current. This is represented by Y, by the admittance. So tell me, what's a current equal to? Look, this current, I have I, the distance x plus delta x, it's equal to Ix plus this current. What's this current? It's this voltage time Y of delta x. It's equal to this voltage time Y of delta x. it's equal to plus this voltage V x plus delta x multiplied by y delta x, y delta x. This is delta x. Perfect. All I do now is I rearrange the system. Can I rearrange this same as what I did before to end up with a limit? Can I do this? Or I can't do this? Let's think about it. So tell me, guys. I'm gonna rearrange this. I do the same as what I did before. The derivative, when delta x goes to 0, I will have the limit. I will have dix. In this system, I have dix over dx is equal to y vx. That's what I end up with the limit. Now, let me write this in here. I will have dix over dx is equal to y vx. What do I have? I have two first order equations, two first order differential equations with two unknown. Two first order equations with two unknown. Now, what will happen if I go ahead and I derive these equations? I want to derive this equation. What will happen when I derive these equations? When I go ahead and I derive these equations, d of vx over dx is equal to z ix. I derive this equation, so I'll have d squared vx over dx squared, it's equal to z dix over dx. Look, dix over dx is equal to y vz. So therefore, I have d squared vx over dx squared, it's equal to zy dzy, dix of dx will be equal to vx. It's equal to vx. Now, this will represent for me I have d squared vx over dx minus zy vx, it's equal to 0. This represent second order differential equation with one unknown. So now I can go ahead now and solve the second order differential equations and find Vx. What will be the answer for it? Let's take a moment to digest this information. So how can I find the answer of this second order differential equation? So the answer now, I have to find the d squared vx over dx squared minus zy minus zy Vx equal 0. This is my second order differential equations. The answer for this circuit will be V of x is equal to a1, Vx is equal to a1. The answer for this, if I use the Vx, it's equal to a1 exponential of the x plus a2 exponential of minus. Now this it's equal to square root of zy is called the propagation constant. It's equal to square root of zy, which is known as propagation constant. This is known as the propagation constant. To obtain Ix, now this is Vx. To obtain Ix, all I have to do is recall my previous equation, if you remember. What's Ix equal to? Remember, dVx over dx, it's equal to Zix. If you remember from the first one, from the first system. Do you remember this information? All I have to do now is I have to derive. Now I have Vx. If I do dVx over dx, the answer will be equal to Zix. I derive this one, a1 exponential of plus a2 x. Now I take this and I put it down. That's what I did. I take the z, put it down to find Ix. To find Ix. Now, I will have to rearrange. I will recall this. The answer for this one now will be equal to Ix. If I recall this definition, Ix will equal to a1 exponential of minus divided by Zc. Zc is a square root of z over y. Zc, the definition of Zc, z over y. Z over y, and this is called the characteristic impedance. This is known as the characteristic impedance of my system. Please, it's very important to note. It's very important to know the propagation constant and the characteristics impedance. The characteristics impedance of the system. It's very important to know these two elements. It's very, very important to know these two elements when it comes to our calculations. Let's fix the light a little bit. It's very important to know these informations. Okay, so now I have Ix and I have Vx. I define what's a propagation constant, I define what's a characteristics impedance. Perfect. All I have to do now is I need to find A1 and A2. From differential equations, how do I find this constant, these two constants? Is by having a set values. by the boundary conditions of my system. What's my boundary condition of my system? Let's first use when I have at x is 0. Let's look at when x is 0. So let's now do the circuit at x is 0. At x is 0, when x is 0, VR is equal to V0 and x is equal I0. That's how I determine my system. So at x is 0, what do I have? I have VR is equal to A1 plus A2. It's equal to A1 plus A2, isn't it? At x is 0, I apply into here, put 0, so now I have V0, it's equal to A1 plus A2. When it comes, which is equal to this, VR. Perfect. When x is 0, I have A1 minus A2 over, this is known as IR. I have IR, it's equal to A1 minus A2 divided by ZC. This is the two conditions, isn't it? These are the two conditions. All I have to do is, now I have VR in respect of A1, A2, IR in respect of A1, A2, and ZC. All I have to do now is to take A1 is a function of VR and IR and the ZC as well, and A2 as a function of VR, IR, and ZC. Okay, that's what I want to do now. I want to take A1 as a function of VR, IR. I want to take A2 as a function of VR and IR, and this will give me V1, A1 is equal to A1 is equal to VR plus ZC IR over 2, and A2 is equal to VR minus ZC IR over 2. So after I did the calculations, all I did is I solved these two equations to make sure A1 what's equal to A2 what's equal to in respect of VR and IR. Is that clear so far? Now, all I have to do is recall Vx. I will put Vx in respect of VR and IR. All I have to do now is I have to take these equations. I will take this, put it into here. This, put it into here. I need to find Vx. It's equal to something multiplied by VR plus something multiplied by IR. That's what I have That's what I have to do. So now what I do is, if I do the calculation, that will be the first one. The second one, this will be and that will be the second one. That will be the second one. That's for Vx equal to this plus this. Now I do exactly the same. All I do now is I will take A1, replace it into E, and I take A2, replace it into E in respect of Ix. Because my aim is I need to find Ix, it's equal to something multiplied by Vr plus something multiplied by Ir. That's my aim. That's my aim. Can you see what I'm trying to go? I'm trying to go to what I learned before. Vs is equal to AVR plus BIR, and Ix is equal to CVR plus DIR. That's what I'm trying to go to. Is that clear? So if I do the calculation, I end up with 1 over ZC exponential of this is what's multiplied by VR, and the second one will be equal to all I have to do now is I will have to recall the definition of a cosine hyperbolic and a sine hyperbolic. If you remember, cosine hyperbolic and the sine hyperbolic. This will give me now A. This will give me A equal to D, as you can see, they equal. It's equal to cosine hyperbolic of can you see this? Yep, it's shown clear. And then I can do B. This is B. Now I can call B. It's equal to ZC sine hyperbolic. It's equal to ZC. It's equal to ZC sine C it's equal to 1 over ZC sine hyperbolic. C it's equal to 1 over ZC sine. These are the 4 elements A, B, C, and D for a long transmission line network. For a long transmission line network, these are the system that I required for me to find. Is that clear? Is that clear, guys? Let's hope. If you have any question, please note down, and we will solve this question during our example session. Take a moment to digest this information. Take a moment to digest this information. Let's do an example now, before we finish this session. We have a three-phase 500 kilometer line where Z it's equal to 0.03 plus J 0.35 ohm per kilometer. Why? It's given to be J 4.4 10 to the minus per kilometers. Question number one. Find ZC. Question number one. I need to find ZC. Question number two. I need to find the propagation constant. Question number three. I need to find the A, B, C, D of the line. Now, what's A, B, C, D? Let's put the definition of each one of them. What's ZC? ZC is square root of Z over Y. It's equal to ZY. A, it's equal to cosine. Now X is L. In my case, X is the length L, which is equal to D. B, it's equal to ZC. Remember B? It's equal to ZC sine hyperbolic. It's equal to ZC and D 1 over ZC perfect. All I have to do now is I plug in, I divide by this to end up with ZC. I divide Z over Y to end up, I will end up with 282 angle minus 2.4. 282. The angle will be minus then the propagation constant, if I apply the propagation constant 0.622, so all I did is I divide this value by this value. That's all I did. And I don't have to worry for ZC about the multiply by 500 because it will go. Now, when it comes to ZY, I have to take into consideration the length because I have to multiply by the 500. Now, A, I apply this, so I say A, it's equal to cosine. This is 500. This already found, what is it? Now, what's a cosine hyperbolic? I call in this. That's what I found. We all know how to find a exponential of this. And I follow the rest, and I will end up with the following answers. A equal D. I have A equal D. The answer of A and D will be 0.813, angle of 4.37. C, the answer of C is 164.6, angle of 85. And D, 2.06, angle of 90. Remember, A and D has no unit, C is and this is Siemens. I put the equation for you so you guys can go ahead and practice. So you can go ahead and practice these values. I hope that's clear, and this will conclude the transmission line performance under long transmission line conditions. Let's digest this information and let's now do a joint program together.